Hi everybody. So this section 4.3 is about the monotonic functions in the first derivative test. Um, and so basically a monotonic function is a function that's always increasing or decreasing. So again, it can kind of wiggle a little bit, but it just can't have any hills or valleys, right? So this would be a monotonic function, right? Because you can see, although it is wiggling a little bit, right, it's constantly always going up. Or if you have a function that's always going down, those functions are said to be monotonic, right? This would be monotonically increasing. This would be monotonically decreasing. Um, Here's another corollary to the mean value theorem. Suppose that f is continuous on some closed interval, and you can find the derivative everywhere in the open interval containing the endpoints. Then the derivative of the function is greater than 0, right? So that would mean that the slope is positive each point, then f is always increasing on AB, right? So that kind of makes sense, right? If the slope is always positive, it should always be increasing. If the derivative is negative, right, it should always be decreasing. So let's look at the first derivative test for local extrema. And suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing the number C we're looking at, except possibly at C itself. So you may not be able to find the derivative at C. Moving across C from left to right, if the derivative changes from negative to positive, right, goes from negative to positive, then you have a local minimum, like here, right? So here the slope's negative, there it's positive. If the derivative changes from positive to negative, like here, then you have a local maximum. And if f does not change sign, like say here or here, then it has no local extrema at C. So again, that kind of makes sense. So as an example, let's say we want to find all the intervals of increase or decrease for this function. Now you already kind of know what this, you might already know what this function looks like, so doing the derivative for this one might be kind of silly, but remember the derivative for this would be, you can think of this as x to the minus 1, right? And so if you take the derivative of that, right, you bring down the negative 1 in front and then reduce the power by 2, which would give you x to the negative 2. So the derivative would be given by that, right? And then what you can do is just test the derivative on either side of the critical points. So no matter what number I plug in for x, this is always going to be negative, so the slope will be negative here. And then if I pick some number greater than 0 and stick it in for x, the slope will be negative there, so the slope is always negative, right? And if you think about what the graph of 1 over x looks like, that makes sense, right? Because it's always decreasing. Let's maybe look at a slightly more complicated function. Find all the intervals of increase or decrease of this function, 1 over x squared. So take the derivative, which would be negative 2x to the third. And so the only critical value there is 0. So check the slope on either side, right? If you pick some number, some negative number and put it in for x, like say negative 1, you'll get a positive number for the slope. So the slope will be positive there. And if you pick some number to the right of the critical value, say positive 1, and stick that in for x, or positive 1 million, or whatever you want, right, you'll get a negative number, right? And so the slope will be negative on that side. And that kind of makes sense, because if you think about, what the graph of 1 over x squared looks like, it should always be positive, right? So on this side, the slope will be positive. That side, the slope will be negative. So let's look at another example. Let's say you take the derivative of some function. We don't know what the function is, but you get this for the derivative, right? What are the critical points of f? On what intervals is f increasing or decreasing? And at what points, if any, does f assume a local maximum and minimum? So again, if you look at the critical values, right, the critical values are where the derivative is 0 or undefined. So the critical values in this case would be 2, negative 4, negative 1, and 3, right? Whatever numbers make the top and bottom of the function negative. So just mark the critical values in the number line, right? So in this case, you've got -4, -1 is somewhere over here, 2 is here, and 3 is here. And I'm not saying this is proportional or anything. But then just pick a number in each interval and see what it does to the derivative, right? So if you pick some number less than -5 and stick it in for x here, right, you'll get like a -7. So this factor will be negative, whatever it is. Doesn't matter if it's negative, what the numerical value is. If you pick -5 in here, that'll be negative. Put some negative number in here, that'll be negative. And then put some negative number in here, that'll be negative. And so a negative times a negative divided by a negative times a negative will give you a positive. So that means that the slope is positive over here, right? Then pick some number between -4 and -1, like, I don't know, say -2, right? And put that in for x, right? So this will give you a negative here, positive there. -2 will give you a negative there. And -2 will give you a negative there, right? So you'll have a negative times a positive divided by a negative times a negative. That'll give you a negative value. And then do the same thing here, right? Pick some number between -1 and 2, like say 0, right? That'll give you a negative, positive, positive, negative. So that should give you a positive value there. Normally this will alternate positive, negative, positive, but not always, so you got to be a little bit careful, right? Pick some number in here like 2.5, stick that in for x, right? I think that'll give you negative. And finally pick some number bigger than 3, right? Like 4, that should make all these things positive, so you'll have positive there. So wherever the slope is positive, right, the function is increasing, and wherever it's negative, it's decreasing, right? So the function will be increasing on this interval from -∞ to -4, from -2 to 2, and 3 to infinity, and then it will be decreasing from -4 to -1, and 2 to 3, right? So then we'll have a local maximum, right? I guess wherever it's positive on one side and negative on the other side, right? So or positive to the left and negative on the right. So like this would be a maximum here, right? The function's going to go up like this. When it hits -4 on the x-axis, then it's going to go down. So that would be a local max at 4 and also at 2. And then looks like it will have a local minimum, which I guess I forgot to write down here. Looks like it will have a local, well, I guess the function's undefined at these points, right? At -1 and 3, right, you're going to have asymptotes there. So it looks like it doesn't have any local min. All right, because the function isn't defined there. So that's kind of what you want to do for the problems in that section. Let's maybe look at another example. So let's say we want to find all the local and absolute extrema in intervals of increase or decrease for this function. Now I've got the graph over here. Let's pretend we don't know what the graph looks like, because again, you may not be able to use a graphing calculator on these sorts of problems on the exam. So what I want to do first of all is take the derivative of this function, and I guess I'm going to factor it here first, but when I take the derivative, I'm just going to use the rule here, right? So I'll just bring the 5/3 down, reduce the power by 1, bring the 2/3 down, reduce the power by 1, and I can simplify that by adding the fractions together to 5x minus 6 over 3x to the 1/3. So the critical values there will be wherever the top and bottom are 0, which would be 6/5 and 0. Right, so those will be my critical values. So pick a test point in each region and throw it into the derivative, right, not the original function. Factoring it like this, I guess, might help you find out where the zeros are. But plug it into the derivative. So if you pick some number that's less than 0, like say some negative number, and you stick that in for x, right, that the top will be negative and the bottom will be negative there, right? So the slope should be, yeah, sorry, this should be positive here, right, not negative. And then pick some number between 0 and 6/5, right? Like, I don't know, 1, put that in for x, you'll get a negative on the top, positive on the bottom, so it'll be negative there. And then pick some number bigger than 6/5, like say 2, right? You'll get 10 minus 6 on the top, that'll be positive. The bottom will be positive, so you'll get a positive there, right? So, and then the function is undefined at 0. So I guess if you graph it, right, you should get something that looks, or sorry, the derivative is undefined at 0, not the original function, right? So if you look at it, right, it's going to do something kind of like that. Okay, let's look at another example. Let's say we want to find all local and absolute extrema and intervals of increase or decrease for this function. So again, go ahead and take the derivative, right? Bring the 4 down. This is your derivative. You can factor out a 12, and then this can also be factored using grouping or whatever you want into x squared minus 0.01 and x plus 10. So the critical values then would be negative 10, and then the square root of 0.01, which will be 0.1 and negative 0.1. Just a note here that if you do plug negative 10 into the function here, you get negative 9.987. But the critical values, again, would be negative 10, negative 0.1, and 0.1. And then check the slope of the derivative in each one of those spots, right? So here the slope will be negative. Between negative 10 and negative 0.1, it'll be positive. Between negative 0.1 and positive 0.1, right, you could stick a 0 in there. You'll get a positive times a negative times a positive, so it'll be negative in there. Finally, pick some number bigger than 0.1, like 1, right? You'll get a positive times a positive times a positive, which will make the slope positive there, right? And so if you look at the graph, kind of hard to see here, but this is the function here. I couldn't really graph the whole thing. So for one thing, I think this is not supposed to be the derivative. I think this is supposed to be the original function, right? The height of the function at negative 11 is negative 145.88, right? So it's way down here, so I can't graph the whole thing. But here's the graph coming in here. It's kind of hard to tell the slope here, but this is negative, comes down, and then sort of bottoms out at like negative 10, and then it starts to come back up, right? So here the slope is positive till you hit 0.1, and then you can barely see it here. So this is an example of a problem where if you use your graphing calculator, you might not notice this here, right? But it goes down a little bit until it hits 0.1, and then it goes up again, right? So in this case, the intervals of increase then would be from negative infinity to, or intervals of decrease, right, would be negative infinity to negative 10, and negative 0.1 to 0.1 when it's going down like that, and then increasing between negative 10 and negative 0.1, and increasing from 0.1. Okay. Here's another example. Let's just do a couple more examples, and then I think that'll finish off this section. In fact, I think this is the last one here. But we're basically going to be doing the same thing for this one, right? So we want to find the intervals of increase and decrease for this function. So again, take the derivative, try to figure out where the derivative is 0. Secant squared is never going to be 0. But tangent of x minus 1, right, that'll be 0 at, say, pi fourths. And remember, we're doing this in a closed interval, so I'm only interested in the interval between negative pi halves and pi halves. And so if you look at the slope there, right, so again, if I make my cut point at pi fourths here, if I pick a value to the left of pi fourths, that will make this number negative here. And if I pick a value to the right of pi fourths, it'll make the derivative positive, right? And you can kind of see that from the graph, right? Here's the graph coming in here. Here's negative pi, or here's positive pi fourths, and then it goes up like that. And that should be the only value between negative pi halves and pi halves. And you can see that that's a local minimum. All right, well that should wrap up that section. So the next section we want to look at in 4.4 is concavity and curve sketching. And this will deal with the second derivative, just like the last section dealt with the first derivative.